Hello, this is the first of a two-part series of videos on basic geostatistics. I want to talk a little bit about geostatistics themselves, and I also want to talk about a little bit of its relevance to groundwater modeling, both how we can use geostatistics to pursue groundwater model predictive uncertainty, but also some of the insights that geostatistics provides into what groundwater modeling can and cannot achieve. But first, let's start with a bit of basic statistics. I'm going to cover a few slides that are in fact covered in another video, but I'll cover them from a slightly different perspective. Let's start by considering a random vector x. Now this random vector we're considering has two elements. It's got a dimension of 2. Its two elements are x1 and x2. And x is a random vector. Random because the elements are random. So, a random vector it's random because its elements are random. And as such, it can be characterized statistically. And that's what we're looking at just at the moment, how to characterize a random vector made up in this case of two random elements. Now the sort of random vectors that we're talking about in geostatistics will have dimensionalities far greater than 2, but looking at just a dimension of 2 allows us to draw pictures which can indicate what we're trying to do through the random vector characterization process. Suppose then that I sample that random vector, that I have a statistical characterization of x, the random vector x, and that based on that statistical characterization I generate random samples. And on each occasion I plot x1 and x2 in two-dimensional random space. I come up then after 1,000 samples with a cloud that looks like this. Now to obtain a joint probability density function for little x1, little x2, I can draw squares all through this two-dimensional domain, and I can come up with the joint two-dimensional probability distribution of x1 and x2. This is just a bell-shaped curve in two dimensions because I am talking about multi-Gaussian random variables. Now let's look at x1 and x2 individually. Suppose that I want to come up with the probability density function just for little x1. So notionally I'd count the number of dots under each of these rectangles, and there is my so-called marginal probability density function for x1. This is the probability density function where I don't care what x2 is, it's just x1 on its own. Because it's a multi-Gaussian probability distribution, it can be characterized by its mean and its standard deviation. And also, because it's a probability density function, the area under the curve is 1. So there's its mean, or its expected value. And the standard deviation, as everyone is familiar with, tells us something about the wiggle room about that expected value. I can do the same for x2. I can count the dots in these horizontal rectangles, and then I can come up with a probability density function, the marginal probability density function for x2. Because it's multi-Gaussian, it can be completely characterized by its expected value, that is its mean, and by the wiggle room about that mean, the standard deviation. Now let's look at the concept of conditioning. So there's x1 on the horizontal axis, x2 on the vertical axis, and this is the cloud that is the outcome of sampling this joint probability density function comprised of the random vector x, which is itself comprised of little x1 and little x2, the two elements of the random vector x. Suppose that I know x2. Suppose that I go to one of these dots, a random sample of x1 and x2, and somehow or other I ascertain the value of x2. Now, what does that tell me? Because there's an obvious statistical relatedness between x1 and x2, knowing x2 tells me something about x1. It actually conditions x1. That's the expression that's often used. To look at the probability density function of x1 conditioned on x2, I can again sample or count dots. I could draw the so-called conditional probability density function of x1 conditional on x2 being equal to a. And from that I can get the conditional mean of x1 and the conditional standard deviation of x1. So knowing x2 has done a couple of things. It shifted the mean, for if I know nothing about x2, it shifted the expected value of x1, the mean of x1, from here to here. And it's reduced the standard deviation of x1. That is, I'm more certain of x1 than I would have been if I hadn't sampled x2. This is the effect of conditioning. Knowing x2 does not tell me x1 because they are random after all, but it has information. And what's the definition of information? The ability to reduce uncertainty, and sampling x2 has reduced the uncertainty of x1. And the same logic applies if I were to know x2 equals b or x2 equals c. I can draw up a conditional probability density function for x1. I will have a mean, an expected value for x1 that is dependent on the value of x2, and the uncertainty associated with x1 will be less. So, what are the repercussions of this? Well, an immediate repercussion is that if I'm going to characterize a multi-Gaussian random vector, or any random vector that's got more than one dimension, and a vector does have more than one dimension, that's the definition of a vector, then I need not just to characterize the variability of its elements, I need to say something about the statistical interrelatedness of its elements. That is, the ability for knowledge of one to tell me something about the other. So here, to characterize the random vector x, I can characterize x1 with its mean and standard deviation. There's its mean, normally represented with an underscore under the symbol for the variable. And instead of writing standard deviation here, I'm writing variance. Variance is simply the square of standard deviation. Variance is a little bit easier to handle when we're describing statistical properties. Under certain circumstances, variances are additive, standard deviations are not. So we often talk about variances rather than standard deviations. I can characterize x2 in a similar way, mean and standard deviation. Now I turn my attention to the actual vector x, comprised of x1 and x2. These are its elements. To completely characterize statistically the random vector x, I need the means of its elements, And I need a two-dimensional, a 2 by 2 matrix, sometimes called the variance-covariance matrix, often just called the covariance matrix, which gives me a description of the variability of the individual elements of the vector x, x1 and x2, and of their statistical interrelatedness. The diagonal elements of the covariance matrix are the variances of x1 and x2. I'm using two subscripts here in harmony with matrix notation, row, column. So here we have the variance of x1, the variance of x2. And off diagonal we have sigma 1, 2. This is the covariance between variable x1 and x2. This will always equal this. Sigma 1, 2 will always equal sigma 2, 1, making this matrix symmetrical. But the magnitude of these off-diagonal elements of the covariance matrix tells me about the ability of x1 to condition x2 and the ability of x2 to condition x1. So it's these off-diagonal elements that tell me about the ability of one variable, knowledge of one variable, to condition the other. The information content that x1 has about x2 and vice versa. And that'll be related to the ratio of the axes of these clouds, how much longer one axis is than the other, and also the angle that that cloud of points makes with either one of those axes. So there I have it, the vector of means and the covariance matrix. And for a multi-Gaussian distribution, if x belongs to has a probability density function which is multi-Gaussian, if I know the means of x1 and x2 and I know that covariance matrix, I know all that I can know about the random vector x. So let's look at this covariance matrix for just a little bit longer. Often we denote it by C brackets x, the covariance matrix of the random vector x. If x has two elements, this is a 2 by 2 matrix. If x has three elements, it's a 3 by 3 matrix, etc. It's always symmetrical. It's always positive definite. And that means for any vector x, this product xt cxx is always greater than naught if the vector x has any element that's greater than 0. This ensures that probabilities are never infinite. It ensures that they're never negative. So that just gives us a brief introduction to statistics, or a brief refresher on statistics, and an introduction to the concept of conditioning. And that will become more important when we consider regionalized random variables, which is the subject matter of geostatistics. So now let's apply the concepts that we've just been talking about to so-called regionalized random variables. Suppose we have a model domain, the domain of a groundwater model, and within that model domain there are many cells. Each one of those cells has to be given hydraulic properties for use in the groundwater model. Well, let's just, for simplicity, restrict our attention to hydraulic conductivity. So we have to endow this model domain with hydraulic properties, hydraulic conductivity, which reflects what we know about those properties and reflects what we don't know. That is, we have to give hydraulic conductivity a statistical characterization. And this is born of the fact that we know something about what's under the ground, but we don't know everything. We don't know the value at every point, but we do know that there is the potential for variability at every point, and there's the potential for heterogeneity throughout the model domain. So in giving properties to our model, we have to come up with a value of hydraulic conductivity in each cell. In cell I, we have to come up with a Ki, hydraulic conductivity in cell I. In cell J, the same applies, and throughout the model domain. Collectively then, once I've given a hydraulic conductivity to every cell in that model domain, I have come up with a high-dimensional random vector K. And the dimensions can be very high if my model domain has thousands of cells and the dimensionality of that vector K is thousands. It has thousands of elements. So there's my vector K. And I'm acknowledging that it's random. Random because I do not know the value of hydraulic conductivity in every cell. However, my ignorance isn't complete. I know something. I know the expected value in the statistical sense because I've done some site characterization. I know the geology that prevails in that area. And I know that while there will be heterogeneity, because earth materials are always heterogeneous, there'll be some limits on how much variability can happen in a spatial sense. If I know a property at one point, then I know something about what the property will be at the next point, a point that's close to the sample point, and a little less about what the property will be further from the sample point. But I know something. I know that there's a spatial correlation between those properties. So between the fact that I know something, but I don't know everything, and the fact that there is spatial correlation between properties, this makes it a relatively straightforward manner to characterize hydraulic conductivity as it is distributed throughout that model domain as a high-dimensional random variable, and to apply the principles that we've just been talking about in characterizing that variable and in making use of that statistical characterization to do some pretty useful things. So, I have a high-dimensional random vector K. If I'm going to statistically characterize K, I can use its mean. That is, the mean of all elements, to give me the mean vector K. And I can use its covariance matrix to characterize the variability of K. Now this starts to get a little bit problematical, because if I've got a very high dimensional vector K, then the dimensions of this covariance matrix are just as big, but in two dimensions. So if I have an m-dimensional random vector K, I have an m by m covariance matrix. And I have to find a way of simplifying this if I'm going to make it usable. We'll get to that in a moment. But just recall, at the moment, that the diagonal elements of that covariance matrix characterize the variability of the hydraulic property. The variance, that's the square of the standard deviation. And the off-diagonal elements characterize the correlation between the elements. Now let's have a look at that. How can we make this description a little bit more simple? Here I've got a matrix with tens of thousands, maybe millions of elements. I do not want to have to supply these individual covariances one by one. We need to look for a way to be able to populate this covariance matrix quickly, based on some fundamental principles which make sense geologically. And a useful characterization, which we'll talk about later, is often approximate, and that's got some problems which we'll also talk about later. But for the moment, let's make an assumption that the correlation, if I have a measurement here and a measurement here, or when I'm looking at the hydraulic property here and here, let me make the assumption that the correlation between K as it exists here and K as it exists here is a function of the distance between them. So I can define a correlation length. I will assume that knowing the value of the property here informs me, provides information of the value of the property here, because there is statistical interrelatedness between properties that are close together. It's not completely independent random. It's not chaos down there. While there is variability, there are limits on the extent to which variability exists. In fact, I am assuming that knowing something here tells me something about here, and less as I move further away from knowing something about here. I can make it a little bit more complicated. I can say that knowing something about here tells me more in this direction than in this, simply because there tends to be greater continuity of properties in this direction than in this. And that's the case in many geological media. They are anisotropic. But the point here is that I'm making an assumption that covariance between the properties at different points is a relatively simple function of the distance between those points. Or to put it mathematically, I'm assuming that Cij, the covariance occupying row I, column J of that covariance matrix, is a function of the distance between the points that row I and column J represent. That is, the distance between point I and point J, possibly with direction taken into account. But let's, for the moment, assume an isotropic medium, and it's the covariance between 2 points is a function only of the distance between them. Now, if I know a function, if I can come up with a simple function that describes covariance as a function of distance, then population of this matrix becomes easy. I no longer have to know tens of thousands of independent covariances. All I have to know is the function which relates covariance to distance and the distance between the points, the centers of the cells of the model domain. And then I have a complete statistical characterization of the variability of hydraulic properties, or in this case hydraulic conductivity, throughout the model domain. Of course, in filling that matrix, in coming up with a function, we've got a fundamental rule we have to obey, that is that that matrix remains positive definite. And as we said before, this ensures that all probabilities are positive and finite. Now once we've done that, once we've come up with a statistical characterization of the variability of a hydraulic property beneath our model domain, well, then we can do some statistical things. For example, we've now got a high-dimensional probability density function. We can sample that. We can come up with random realizations of properties within our model domain, all obeying those fundamental concepts that they've got the same mean and that variability and covariance is described by that covariance matrix, which is based on the premise that covariance between 2 points is a function only of the distance between them, and presumably I have come up with a function, which we'll talk about shortly, that gives me that variability, that covariance as a function of interpoint distance. Not only can I generate random realizations, I can also use the phenomenon of conditioning that we talked about a little while ago. I can come up with random realizations of hydraulic properties that are conditioned by the fact that I may have sampled those hydraulic properties at one or a number of points in space. So now my random realizations all have the same values at the sample points, but more than that, they all have limited variability in the vicinity of those sample points because of the fact that I've sampled at those points. And, as we discussed, the effect of conditioning says that I have information by sampling here, I have information about any point with which the sample point shows correlation. Therefore, in all of these conditional realizations, there will be less variability in the vicinity of sample points than further afield, where the conditioning effect of the sampling is very small, or zero, by virtue of the fact that covariance runs out, becomes zero when the distance between 2 points is large. Now that's one thing I can do once I have a geostatistical characterization of the variability of a hydraulic property throughout the model domain. Another thing I can do is I can use statistics as a basis for interpolation between sample points. And this interpolation is then done in a special way. When I interpolate, I use statistical principles to come up with an interpolated value at every point in space that is actually the value of minimum error variance, the best linear unbiased estimator of the value between the points, the expected value between the points in a statistical sense. And I can come up with the uncertainty of that estimate as well. So the thing that geostatistics is doing for me here is giving me a special way of interpolation between sample points that gives me some very powerful properties of the interpolated field and gives me the uncertainty associated with the interpolated value as well. And the method of interpolation that's based on geostatistics, as I'm sure you all know, is called kriging. But it's also called estimation or interpolation. There are many interpolation methods. Kriging is that which is based on geostatistics. So here's another model domain, and here are some random realizations of a hydraulic property throughout that model domain. And suppose that I have samples of that property at, in this case, 5 points. Well, applying the concepts that we talked about earlier, that if I know the value of a random variable, one random variable among many, and if there's any covariance that exists between that random variable and another, then I have the ability to come up with, to calculate a conditional expected value for the other random variable by virtue of knowing the value of the first random variable. Using the principles of conditioning, I come up with a conditional mean and a conditional standard deviation of the other random variable, and because these points pertain to different points in space, that is actually interpolation between sample points. So, here is my interpolated, my kriged parameter or hydraulic conductivity field. Notice that it's quite smooth compared with the real thing. The more sample points that I'm interpolating from, the more variability I get to introduce into this model domain. But the interpolated parameter field is still quite smooth. It doesn't pretend to be reality. What it pretends to be is the minimum error variance estimate of reality, something that's approaching the center of the probability distribution of reality. So at this point here, we're not saying that this is the actual value of hydraulic conductivity here. We're acknowledging that it's still uncertain, but by virtue of conditioning by the sample points, it's less uncertain than it would otherwise be, and this is the value that would be at the center of the probability distribution of hydraulic conductivity at this point. And as we have more sample points, we can introduce more variability, but we still have a smooth interpolated parameter field. Smooth for a good reason, for a good statistical reason. This is the expected value of the hydraulic property between the sample points. So, just to get it straight, if we use geostatistics as a basis for interpolation, that is Kriging, we come up with a unique parameter field, a parameter field with special properties. Kriging gives us uniqueness. It gives us a parameter field of minimum error variance between the sample points. On the other hand, we can use the same theory to generate realizations of the hydraulic property fields between the sample points. This and all of these have in common that they have the same values at the sample points. However, these parameter fields show variability somewhat restricted in the vicinity of sampling points because of the conditioning effect of those samples. But there are an infinite amount of these, an infinite number of these that we can generate. And if we were to take the average of all of these, we would end up with this. And that is what Kriging tries to give us. That is the best linear unbiased estimate of the hydraulic property between the sample points, the expected value, the value of minimum error variance. So in summary then, by treating Earth properties statistically, we get to do some pretty useful things. Now we're acting under the premise here, there are assumptions here, assumptions which are probably violated to a greater or lesser degree in just about every geological medium, but nevertheless not violated so badly in many places that we cannot use these principles. The assumptions are that stationarity, as it's called, that the covariance between 2 points is a function only of the distance between them, and then that function doesn't vary throughout the domain of a model. That allows us to easily populate a covariance matrix. And also the mathematics on which Kriging is based and generation of those random parameter fields, those random hydraulic property fields, we are assuming a multi-Gaussian assumption, a very high-dimensional multi-Gaussian assumption, but a multi-Gaussian assumption nevertheless. But if we make those assumptions, we can do some useful things. We can generate realizations of hydraulic properties throughout a model domain. They can be conditioned on the fact that at certain points within that domain, we have measurements of those properties. We can interpolate between those measurement points in a way that gives us an estimate of the property between those points that is of minimized error variance. And we can quantify the uncertainties of those estimates. Now we can get more sophisticated, but we won't be getting more sophisticated in this video. There are different types of kriging. We can relax the assumption that we know the mean of a hydraulic property everywhere, and by doing that we undertake a type of kriging called ordinary kriging. What we do have to know is the dependence of correlation on distance between sample points, which we will characterize with a thing called a variogram, which we'll talk about shortly. But by relaxing the assumption that we need to know the mean of the hydraulic property everywhere, we can undertake a type of kriging which accommodates that, called ordinary kriging. If we do know the mean everywhere, the way we krige can accommodate that knowledge. Slightly different equations, that's called simple kriging. We can undertake kriging with a trend. If we know that there is, for example, a linear variation of hydraulic properties from east to west through our model domain, we can estimate not just the hydraulic properties between sample points, but also the function that describes that linear or more complex variation of the hydraulic property throughout the model domain. We can extend the concepts, which we've just been talking about, to include not just one but two or three random variables which are correlated with each other. And in doing that, we undertake, if we're undertaking interpolation, we're undertaking co-kriging. And we can extend these concepts further to indicator variables. An indicator variable is a variable that's either 1 or 0, black or white, categorical. In the geological context, it would describe whether the particular geology, the particular formation at a certain point is this formation or another formation, or this lithology or another lithology. We can extend these concepts to on or off type characterization, statistical characterization of the variability of a property throughout the model domain, that property being whether we have this lithology or that lithology at each point within the domain. So let's look now at how we can actually characterize the stochasticity of a medium in which we want to describe geostatistically. So here's our random field in our model domain, and what we want to do now is to come up with a geostatistical description of variability of the hydraulic property that allows us to do the things that we've been talking about up to now: random field generation, conditional random field generation, kriging. Now, as we've said, normally in geostatistics in statistics we have a mean value and a covariance function. This then gives us a complete characterization of the stochasticity of a random vector. We could do this in the geostatistical framework, but it is a little bit more convenient to use another description of stochasticity for regionalized variables. And that alternative description is embodied in a thing called a semi-variogram. And by using this, there are certain conveniences accrued to us by how we come up with the actual equation for the semi-variogram, and in the fact that we can dispense with the need to know the mean value everywhere throughout the model domain. We can use just the semi-variogram as a basis for kriging and random field generation. This is the equation for the semi-variogram. Semi by virtue of the half in front of the equation. E means expected value. Here's the property at a certain point minus the property at another point squared. So the definition, gamma h, gamma it's nearly always referred to, the semi-variogram, gamma as a function of h, that is, this curve as it depends on h, is equal to half the expected value of the property at a certain place minus the property at another place squared. So we take the difference between these properties, square them, and the expected value of that squared difference divided by 2 is the value of the semi-variogram as it pertains to the distance between them. Once again, we maintain a fundamental assumption that makes all of this doable, that the statistical interrelatedness between the properties at any 2 points is a function only of the distance between them. Now, before we talk about a quantitative description of a variogram, that is, a mathematical expression which we can use to describe that curve, we'll just mention a few qualitative descriptions. So the first thing is the range. Now, as I just said, the variogram, the description is quite intuitive really. The fact that this curve rises and then flattens out is just a reflection of some pretty obvious properties of a random medium, of a heterogeneous medium in general. That if I know something here, the difference between the property here and here should be smaller to the extent that these 2 points are close together. The closer together they are, the smaller should be the difference in properties between them, hence the smaller the difference in properties squared, hence the smaller the value of gamma as a function of h. The further our 2 points apart, the larger we expect, E for expectation, the larger we expect the difference in properties to be. However, we'll reach a point where that difference doesn't get any bigger, and that reflects the innate variability of the properties within this medium. So we expect a variogram to rise as distance increases and then to flatten out. The place where it flattens out, or gradually flattens out, is called the range of the variogram. The sill reflects the innate variability of this heterogeneous medium. The fact that if 2 points are a long way apart, there's only going to be a maximum certain expected difference between the properties, because the variability of properties within that model domain is not infinite. Finally, the nugget. Normally this is set to 0 if we're using a variogram in groundwater modelling to generate stochastic fields for the use of a groundwater model. It reflects the fact that there could be a difference completely independently random between the hydraulic property at this cell and the neighbouring cell. This can be the case, but normally that's set to 0. So what then is the relationship between the semi-variogram and the spatial covariance function? Here we've got the 2. We started off this video looking at a spatial covariance function because it's more closely related to traditional geostatistics. But now we've moved to a variogram, or a semi-variogram, because it's a little bit more convenient to use in a spatial setting, and it's more convenient to populate, as we'll show shortly. However, in the end, it doesn't matter too much what we need, because the relationship between the two is very simple. Basically, the covariance function is just the variogram turned upside down and migrated so that it is asymptotic to 0, where this is asymptotic to the sill. What this means, quite simply, if we know the variogram, we know the covariance function. As we talked about earlier, if we know the covariance function, we can populate a covariance matrix, we can generate random fields, we can undertake conditioning of those fields, we can Krige, and we can generate conditioned random fields. So knowing the variogram gives us what we want in terms of the things we want to do, which we have talked about earlier. And the same qualitative descriptions of the variogram apply to the covariance function. Okay, so the next question is, how do we come up with a variogram in a real-world situation? Well, let's pretend that we have a lot of sample sites. Then we have the ability, in theory, to build a variogram. So, and building that variogram immediately springs from its definition. So the first thing is, let's look at all points which are a small distance apart. Distance between here and here. Let's go to our database and look at the difference in properties squared through all points which are a certain distance apart. And then we can average those properties, difference in properties squared, and come up with the value of the variogram as it pertains to that distance. We then look at all points which are a larger distance apart. Take the difference in properties from every pair of those points and get the average of the property difference squared, divide it by 2 for that point separation, and we've got another point, empirical point, in constructing our empirical semi-variogram. And we do that for points that are a larger distance apart, and a larger distance apart, and a larger distance apart. And then we fit a curve to these empirical points that we've just determined. Now, in groundwater modelling contexts, rarely do we have the luxury of too many points on which to construct a variogram in this manner. In most contexts that we deal with, we'll only have a few points. And they'll be the sites, for example, where we've done pumping tests to determine estimates of hydraulic conductivity at a point. And then there's the question of how applicable are those estimates to groundwater modelling. So, in our case, we're not going to come up with a complete geostatistical description of the properties of the material which populate our groundwater model domain. That doesn't mean we can't use geostatistical principles. We have to characterize uncertainty somehow. But what it does mean is that there'll be uncertainty in the uncertainty. That does not invalidate the use of geostatistics. Everything we do in groundwater modelling is approximate, including coming up with a descriptor of the spatial variability of hydraulic properties. Intuition can often be our guide. We can come up with values for the sill and for the range just based on knowledge of the geological materials we're dealing with. We know the scale of spatial variability. We can use that to come up with a rough range. And on that basis come up with an approximate variogram. And just keep in mind too that when it comes to Kriging, that is interpolation between sample points, the sill doesn't even matter. So it's the range and the shape of that variogram that's the important thing. And because of all the other uncertainties and errors in groundwater modelling, the error incurred by having to actually guess the variogram based on intuitive knowledge is probably not a large contributor to the uncertainty in the uncertainties that we're able to calculate if we can give a geostatistical description to the properties of the medium through which groundwater flows. So the next question then is, all right, we have to come up with a mathematical description for a variogram so that we can come up with a covariance matrix, well, with a covariance function which allows us to build a covariance matrix easily, using which we can do the things we've talked about earlier, the interpolation, the random field generation. There are a number of functions which are commonly used for this purpose, and they are spherical, power, exponential, and Gaussian. I've plotted them all here for the case where the CIL is 1 and the A value used in each of these equations is 1. These equations all have the right shape. They start off small, they're asymptotic to a value. More importantly, they all result in a covariance matrix which is positive definite. And the importance of that we talked about earlier. So these are the four functions that are often used to characterize a variogram. They're not the only functions that we can use. There are other functions, but these are easy, they're convenient. In certain situations, there are other functions that are better and have that same property of being asymptotic to a CIL and giving us a positive definite covariance matrix. But on many occasions, one of these functions will do. The most popular is the exponential. Why? I'm not entirely sure. Probably a matter of convenience. Finally, before we finish part 1 of this video, let's just look at the question, how do we do it? Well, there's a lot of software around, mostly commercial, that's very good, that does all the things we've been talking about. But I'd just like to draw your attention to some fairly useful software which is free, it's downloadable from the internet, which does all the things we've been talking about and more, and can actually be very useful. A lot of people use it. It's described in this book. The book's not free, but it's cheap. And the software is SGEMS. SGEMS stands for Stanford Geostatistical Modeling Software. The building of the variogram, its use in kriging of various types, in random field generation, and then more complicated geostatistics, which we'll just talk about a little in the next video. SGEMS allows you to do all of that with a nice graphical user interface and a pictorial representation of anything that you've just done using the principles that we've just been talking about. So that's available online. The PES Suite 2, a number of the programs in the PES Suite and in its supporting groundwater data utility suite also rely on some of the principles that we've been talking about. PLPROC undertakes interpolation from pilot points to a structured or unstructured grid. That uses kriging. FieldGen, random field generation, using the principles we've just been talking about, random field generation for a modflow grid. The PPCOV suite of utilities generates a covariance matrix for the use of pilot points in either random field generation or regularization based on a variogram. And the RANPAR suite of utilities allows you to generate random samples of pilot point values based on the covariance matrices generated by the PPCOV suite of utilities. That brings us to the end of part 1 of this series of 2 videos.